Hello and welcome to lecture 11, part 2. So, if you remember from the first half of this lecture, we were starting talking about some additional functional programming constructs. So, in the prior lecture, lecture 11, we talked about things that were kind of one-to-one, things like map or for each were for a collection of things. We applied the function each of them. And then in this lecture 12, or 11, I guess, we've been talking about how to reduce things, right? Talking about both reduce and fold. And so now, in the second half of this lecture, we're actually going to apply them more. So, we'll fire up our notebook. You may remember from before we talked about reduce kind of handling binary operators and fold left and fold right being more specific. We concluded talking about currying, this ability to kind of break up the function arguments into two blocks and apply them partially. And so then a little bit of Scala. So um, we've seen a lot of different things happening, right? We're talking about these various functional programming constructs, which we've told you things like map actually aren't built into language. They're actually uh, methods that happen to exist on these collections we're using. And so it'd be helpful for us to be able to read things like documentation. So to help with that, we're going to look at the Scala docs and talk about how to read these signatures. So this is a certain language they kind of have for describing the way types interact. We can cover this, right? So for example, this tells us that, map will take a function that has arguments of type A and produces some output of type B. Um, there's actually a single argument of type A and it produces a single output of type B. And so this is what you get with a seek. So returns a collection of type B. And you see, for example, for fold left, um, it's given this output type, which may be the same or different than the type it's making, right? So let's go ahead and scroll through. So here we have linked to seek. There's a zillion methods, right? And so of course, reading the text about what it does helps you see a little bit what's going on. But now you also can see more about these type signatures, right? And learn how to read that syntax in this language. Um, so yeah, that's kind of the whole point of this. You may see, like I said, so this equals greater than is like, just showing you a function. Um, there's an additional thing you may see in some of these things like this, where it's a greater than, it seems to be doing some sort of greater than with a colon between two types. This is for covariant and contravariant types. It's a concept we do not need for this course. We do not need for writing Chisel. It's, in my opinion, an overly complicated Scala feature. Yes. What does the arrow indicate? Indicates it's a function, right? So something comes in, something comes out. And so yeah, so for you as a designer, right? It's a good question. You should think about your types, right? If you take a type, you are obliged to take a type. Now you can use things like the require statement or the assert statements to kind of push back and say, you know what, that thing you gave me, I can't quite process the way you want to process it. But unless you put in asserts or requires, it's anticipated or assumed, otherwise take everything from that type. And so Scala makes it easy for you to make your own additional types, and you're encouraged to do that to constrain it more. Good questions. So yeah, so actually, wait. The whole point of that was to show you that, hey, guess what? Map is just another method. Um, cool. So, uh, filling up from last time, we talked about, I talked about reduce with no directions, and they also mentioned fold left. And the question might be, well, what combinations are there? Actually, all six combinations are there. So for reduce and for fold, there is, no direction given, left and right. Um, and so what are the differences? Well, the direction is given explicit evaluation order, right? So if I say reduce left, it's going to go increasing uh, in the index it touches, right? So I think of fold or reduce left or fold left as, going 0, 1, 2, 3 up through the collection. By contrast, um, if I say, reduce right or fold right, that's like, n minus one, n minus two, n minus three kind of going down from the top. And one thing that's worth mentioning is that, so we work with seeks a lot in this course. So seeks have a notion of an order, right? It's something at a certain index. There are some collections that have no notion of an order, right? Like a set, for example. I can say that, my set, I have no two elements that are the exact same value out of that set property. But otherwise, the ordering, is maybe unspecified depending on what set you're using. But you still have these functional operators. And so depending what you're doing, the notion of what left and right is may vary. But fortunately for us building hardware, we're not doing all of the esoteric Scala. We're just doing hardware we need to make good chisel, in which case left and right, thinking about things with an index and a seek is totally right. Um, and so yeah, so in theory, fold left is the most versatile and most general. But reduce is simpler, right? You don't have to give it the initial element. It can just take a binary operator. I find writing the functions for fold left a little bit tedious at times. Um, but sometimes you need it, right? Reduce doesn't handle empty things very well. Fold left handles it a little bit more gracefully, etc. And y'all saw, when do we use fold right or reduce right? Well, we can just call dot reverse and then fold left or fold right, or fold right or reduce right. That's technically slower because it's going to reverse the collection and then apply it. But for the size collections we have in chisel designs, that's totally tolerable. However, if you have the time and interest, yes, use the right version. So let's see some examples. Um, so we've done this reducer before. Originally, we did this with a for loop, right? So we had a var, we're just kind of, going through it, given some things, it'll add them up for us. Perfect, cool. So then if we want to instead use the reduce operator, uh, that works great, right? That's pretty cool. So, hey, we have these things, we're just adding them up, we can reduce, that's cool. If I have one element, how does that work? It works with one. Now, if I say two or zeros, it's probably going to break. Yeah. And I actually require you to have at least, one. Um, but cool. So this is the reduce at work. Let's keep going then. So then we had this, delay pipe from earlier. And so yeah, remember we had a few different ways. This way is recursion, right? So basically you kind of recursively call this helper function. Maybe you don't enjoy recursion. Well, what if we instead recognize the structure, right? Recursion kind of has a structure of repeating this pattern over and over again. What if we use this pattern of fold left, of kind of going through this collection iteratively? That's what we did. So we start with io.in, and then what do? Well, we make a reg next connection, and then the result of this, of course, is the output of the register, which we can then be last con or last connection, and then pass on to the next iteration. Now, what the heck is this I? Well, the question is, what collection are we even iterating on? We're collecting, the collection doesn't even exist. I chose a range instead of the right number of iterations, but the answer is we don't really need this I, but because it exists, that's what we're iterating on. We're still giving it whether we want it or not. So we have to have a function that accepts it, even though we don't actually use it. But yeah, our version with fold left works great. And the cool part is, of course, we can go to zero and does the pass through of the register just fine. It's very graceful for handling different conditions. Um, it works. And so, yeah, sometimes fold left's a little bit trickier to write, but once you get it right, it works. For me, I always have a hard time remembering with these two arguments which one is the one that's kind of carried versus which one's the element. And that's one of those things. Well, guess what? If you forget that, that's what the docs are for, right? And the docs will help you remember which one's which, right? Okay, the result's going to be B, this initial thing's B, and that's kind of remembering what's going on. Cool. So pretty good on fold, reduce. Let's move on then. So there's another helpful function called zip with index, which the name is what it implied. We covered zip last time. We were given two collections. We, interleave them and combine them. And zip with index is I'm gonna now take these collection elements, which are once you have them in isolation, there's no number available, but we actually are going to pair it with its index, right? And so um, you may have seen enumerate in Python. This is very, very similar, right? So, let's kind of build our way through it. We start with a nice little sequence, 5, 6, 7, 8. Cool. But what if in my interactions with this collection, I want to know what element index I'm working with? Here's one way to do it. You could say dot zip and then have something that's the same size as the collection. And you can see when they get zipped together, 5, 6, 7, 8 now has 0, 1, 2, 3 for those that range being zipped within. Such a common thing people do that they put zip with index into the language, right? So I get the same thing with zip with index. Here I called it, with a dot. And that's really helpful. What if, I actually wanted to work on these pairs somehow? So this next example, of course, this produces the same things above, but now I'm going to apply a map to it. And given these, it's going to give us a tuple because we're getting these pairs. So I can, of course, with a tuple do _1, _2 to get access to the elements, and tuples start indexing from 1. So, okay, I can go ahead and multiply them together. Sure, that's fair game. Maybe you'd rather use pattern matching to kind of pull apart your tuple. We can do that. We did that here. In which case, yeah, we can use that case schema to do pattern matching, and we can pull apart the tuple. So in which case, we're getting the original element from L, and then I, which was provided by zip with index. And so different ways of doing that. That's kind of the key idea. I think I have a diagram next. Yeah, here you can see it, right? Given input in blue, we have the indices, and we just go ahead and pair them up. And so there's sometimes it's helpful to have that information available when you're doing iterations. And so this is a really helpful function for that. Cool. Um, so once again, let's keep trying to push boundaries what we can with our functional programming. So remember we did a one-hot priority encoder last week? And we did it a few different ways with either muxes or gates. So here's our with mux implementation, which built this unbalanced chain of muxes with recursion. If we were to look at its output, or a reminder what the one-hot priority encoding does, of course, uh, we're trying to find the least significant bit. The first one is turned on. So you can see, for example, once this one's on, it always wins. But if it's not on, the other ones have a chance, right? And you kind of see who wins. And so we did that with muxes and recursion. We're going to do it with muxes still, but let's do it with the functional programming. And this one's a lot more complicated, right? So let's kind of talk our way through this one. So what are we doing? Okay, we're taking our input, sure. Now, the input is a uint. To kind of be able to iterate on it, we kind of turn it into collection. So right now it's a single number, break into individual bits. So that's what as bools does. Cool, now I have individual bits. And I'm gonna want the indices, because indices are actually something we need is kind of useful. And then, because we did this from least to most significant, we need to reverse this. And then we're gonna call fold left and basically say, okay, well, starting from 0, the things so far. And so given the tuple, of course, is coming from the zip with index. And then, oh yeah, there's the actual element coming from the input and then the index. And you can see make this mux. So basically, if that bit is true, then we want to report this index correctly. Otherwise, kind of keep passing on. This is also going to produce the exact same answer, i.e. it works. It might be a little bit complicated. I don't know. This is obviously more clear or easier than the one above, but we're trying. Yes. Oh, the question is how exactly does this work? So the way this works is basically we are trying to, as you said, it's a one hot output, right? So it's going to be only one bit's true in the output, and so we're passing this mux along. And if you trace the path through the series of muxes, there's going to be a connection from one literal all the way to the output, and the mux can change which literal that is. And so we're creating those literals right here, right? And so whatever index you are, we want that kind of to match. And so yeah, by shifting this over, this is going to have a bit exactly one bit set in this literal, right? It's going to be, one shift over 0 bits, one shift over 1 bits, etc. And so yeah, that's kind of the literals we're setting up in the end. Good question. Um, but yeah, so this is, a little tedious. And we talked about, well, here I called reverse. What if I didn't want to do reverse and I wanted to do fold right? We totally can. Uh, Now the catch about fold right and someone in Scala was either very clever or very annoying in your opinion, they changed the order of the arguments to this function, right? Because you're going the other direction now, the so far thing gets flipped. But yeah, if you do this right, sure, you get the same answer. Instead of reverse fold left, we did fold right. We had to flip the order of the arguments on this portion. This portion, of course, stays the same. But yeah, I mean, I suspect looking at this, you may decide, you can ignore the comments. It's kind of like, two lines replacing, I guess technically four or five lines, but these aren't exactly easy lines, right? These are dense lines, right? There is, one, two functional operators, as well as an API call in there, right? I would not call this super trivial. Um, but we're gonna try it out. We're gonna kind of experiment with it. You'll see in this week's lab, or just say the lab assigned this week for next week, lab four, that where I'm gonna definitely ask you to kind of do a lot of things functional programming. Some of it may be a little bit intentionally overdone, just to kind of give you that experience. The good news is the numbers are small, the collections are small. You can use print statements to kind of see what's going on in that notebook, and play around with things. Cool. Questions? So, let's keep reusing stuff and using functional programming to make things cleaner. So we did this crossbar a week ago. Here is kind of initial starting point. Oh yeah, we have the message. It gets routed through this crossbar, so it's network connection. And then we have the I/O, which is basically just a vector of these ports to do messages. Sure, we've seen this before. So uh, once again, I'm going to show you an example of using functional programming, and we're going to kind of progressively apply it more and more aggressively, and to a point at which maybe we'd agree it goes too far. So as a starting point, uncommented in this code right now is the original crossbar we wrote a week ago, right? So you can see that because this crossbar kind of has all these all-to-all connections, all these input ports need to be able to reach all these output ports. We often get this kind of nested for loop structure, right? Because it's kind of this all-to-all pattern, right? For every input, talk to every output, etc. And we kind of had it on both sides, where we have for every input, now we're considering every output, and then we also have for every output considering every input. And the reason why is we're kind of either propagating information back to the inputs or sending information out to the outputs. And then along the way, of course, we build arbiters. They're declared here, but then they're kind of really connected up mostly, not mostly, but not exclusively, but mostly in the output loops. So yeah, there's these doubly nested loops. So yeah, I mean, of course, we can, from before run this. If we really want to test it, we can see it, passes our tests I wrote. But yeah, the original code was a little bit hairy, but if you appreciate what it's doing, it's actually doing this pretty cool, very parameterized generator where it's actually like, based on these parameters, really changing the internal topology accordingly. It's pretty impressive. So, what can we do? Well, let's kind of look at what we're doing here. For example, here we're trying to grab all of the input readies, and we're going to grab them for every output port. We're going to hit connected up, and then we are going to do that OR reduction and connect it back to the input port. So you may wonder, wait a second, if I'm doing this for every input port, why am I doing the same thing over and over again? There's this subtle detail. We don't want just any ready. These arbiters have a lot of ports, right? So we want a particular, for every output arbiter, right, we want to get the ready signal corresponding to this input port, right? So that's we're trying to do this very careful selection, so to speak. So kind of grabbing all these things and then doing an OR reduction. So alternatively, uh, let's try and do that with the functional, right? And you can see that right here. Uh, so instead of doing the grabbing with this for loop, where we had declare, wire, and grab, that's just this, right? What do? We went through the arbiters. So that's kind of this portion right here. We mapped onto them. In particular, we grabbed for the input port the ready, right? And remember, this is that syntax, we're using that placeholder syntax where rather than saying, arbiter like that, we can just say, that. So yeah, we're going into each of these arbiters, going into their IO, into their input, specifically for IP, which is iterating through all the inputs, and grabbing the dot ready. So this little bit of code basically replaces like that. And then for the OR reduction, we saw this before, we can just call dot reduce. So we get the dot reduce, and now that we've done all of that code, we can just directly assign it to the port without having to actually, name an intermediate variable. So, I can show going to the next slide, and it's still going to pass the test. Yeah, so that works. So this is a case where I think that's pretty cool, right? I wouldn't say this is trivial code; it's a little bit dense, but when it comes to like grabbing signals out of collections, map in within using within Chisel is a really good usage case, right? It really works pretty smoothly, pretty clearly what's going on. Um, that's nice. How about the one below? So the one below, what are we doing? So for every output, we're now going through all the inputs and basically wiring things up. So basically, for all of those inputs, we have to attach them to this particular. So this is the output arbiter, right? We can connect to the input bits for that input, both the bits and the valid. And oh yeah, by the way, there's this extra logic we have in there to make sure it's not just is this input valid, is this input valid, and then of course is it destined for this output port, right? Is it destined for me? Um, okay, so this is a single for loop. How can I do that with functional programming? Well, let's go ahead and see that, right? If we go ahead and uncomment, um, we're going to go ahead and take the arbiter ports. So here we kind of iterate through num-ins. Now we're just taking that collection. We're going to zip with the input ports. And so guess what? There's already a perfect one-for-one correspondence, right? Each of these arbiters have a port destined for the input. The input ports already exist. So here we happen to iterate through this IP variable, iterates through kind of that range, and we kind of accessing the same thing on both sides. Since we're accessing the same thing on both sides, we can just, zip those together, right? And you can see I even labeled them, right? Arbin, ION, and we're going through it. And remember, the point of this loop, for example, is we want to make side effects. We want to do connections. And so here we use the for each, right? Because we care about the side effects. In the prior example up here, we used the map because actually in that case, we wanted the output. We wanted to grab these ready signals, right? So we're kind of showing these functional concepts at work. And then for this valid, we already have the right thing kind of already peeled together. Is iterating through things with the zip. We already have this portion given to us. So great. We can just, connect those over. And then for this logic about making sure it's addressed to me, that's right here, right? So this is a pretty nice reduction. It's actually probably even a slight character count reduction. And once again, we go through this and then, pull it out. It works. So that's cool. Um, so yeah, I would argue here we know functional programming is, if not better, at least worth talking about, right? We've basically replaced a for loop, in this case with a map, because in that case, like I said, up here, the issue was we wanted to not just even though we're making connections, the point of the connections is just for us to kind of build up a thing. We really wanted the results, and the result, of course, was this ready signal. So map is right. Down here, there is no output. It's just we want side effects. We want for each in this case. Cool. Questions? Oh yeah. So the placeholder for reduce, we have two placeholders. Let's remind ourselves what those are. So at this point, this code is going to give us all of the ready signals relevant. So we have a collection of signals, and we want to take the or combination of them all. So before, when we had that problem, we had kind of this hack of taking a vec, turning it into a uint, and then calling it dot or reduction, which is a thing built into Chisel. Alternatively, we just said, hey, let's reduce, meaning take this binary operator. So this operator needs to take two arguments because it's binary, and then apply this operator until there's nothing left. So it's kind of that, unbalanced tree. And so yeah, so in this case, we use the or operator to combine them all. So this is, element A, element B, and they ORs them together. So it actually applies it to this case, what you're really going to get is originally it's going to take two elements, OR them together. Then it's going to take, you know, that output, which is actually an OR of something before, and then OR that with another element. So you kind of keep getting, OR of two elements and an OR of that OR of another element, OR of that OR of another element kind of going in. Cool. Other questions? Okay, so then how about um let's try to do more functional programming. Let's remove four from our lives. How crazy would that be? Um, so let's kind of take a step back, right? So here, even though we're using functional programming, we still kind of iterate across all inputs, right? Iterating across all inputs. How do we remove that? Well, so originally we still have iterating across all inputs. And I here have the code already contracted out for us. So it's just the for loop and then inside of the functional programming. Studying this, think about what needs to happen. Okay, for every input port, we kind of need this connection, but also recognize we kind of need this numerical index in order to not just grab from io.in, but we also need to grab from this thing. And this thing, remember, is an arbiter. So we kind of need that numerical index to grab the right port out of the arbiter. This is one of those cases where we are going to need zip with index, right? We basically need that input port and then that input port number. And great, we can go ahead and take advantage of this thing iterating through it for us. And so, for example, what before was all of this is now just in, ready, okay, map. Uh, but then, this portion is unchanged because this long portion is actually indexing into the right field within that arbiter. So that's going to be unchanged. But yeah, that comes all together. And so for this one, yeah, we turned a for loop into a for each. In this case, for each, of course, because we don't actually take any result. We just are doing a side effect. Um, visually they don't look that different. So I'm not sure this one's a total win. But hey, we tried, right? We tried to try functional programming, right? Maybe the for loop with the functional programming inside is more clear. Maybe. There's some, perspectives. How about down here? So from before the prior slide, we collapsed all this to a for each, and there's a for wrapped around that for each. So what can we do? Well, how are we using that for loop? Okay, where do we use OP? We use OP here, and we use OP here. If we only used arbs OP, we would probably once again get away with like a for each. But because we need OP like deep inside things, like here and here, we're going to need to do a zip with index. So what are we doing? Okay, we're going to go ahead and zip the outputs with the arbiters, like we're going to do here, right? That makes sense. And then zip that with the index. Okay, for each because we care about side effects. So then because the first zip creates this pair, then the zip with index creates the index here. And then we're going to go through. Okay, well then for the arbiter, we're going to go ahead and iterate through the appropriate arbiter input, IO input, and wire this all together. So it's all there. It's kind of a little hairy, right? Remember the original code was two for loops. Now we have two for eaches. So complexity wise, we're in the same ballpark. Um, but yeah, I don't know about you. I think this is complicated, right? If we go back a couple slides, uh, you know, we could have just had two for loops, right? We could have been doing just this, right? Maybe that's more clear. And so, yeah, I think it's one of those things to kind of play around with, right? Always have this kind of dialogue with yourself, and especially when you have a project partner or someone doing a code review for you, what makes things more clear, right? What does more sense? Yes, we'll just share the same hardware. Yes. Uh, now I say that it's an asterisk. The asterisk being technically maybe the Verilog might look different, and the Verilog might look different because of the way intermediate variables may exist and be named. But in terms of those small naming differences in the Verilog, those will not have a material impact in the hardware, especially after a CAD tool's optimized it. Um, so really, yeah, the goal for us is to write code that is clear, correct, easy to work with. Obviously not inefficient, but neither of these two things we talked about change the efficiency. They just change the code expression. Good question. So yeah, so today's example of maybe we went too far, right? I have a fun aside, down here I even attacked this printing debug statement and instead did it with a for each. Yeah, we can, functional program our way through everything we want to for fun. I encourage you to embrace it a little bit in this course to try it out. And then if you have more comfort and familiarity with the more complicated cases, that'll make the easier cases look easier, and then you're more likely to use it. If I only had you do it the easiest cases, the easiest cases were now foreign to you, you'd be like, oh, that's too hard, you're not going to do it at all. And so we're going to definitely overshoot some functional programming stuff, and then we're all going to collectively agree, you know what, this can be overdone, scale it back some. Like I said, a single map or a single for each is often really clear, really helpful. And we'll see some more examples in the following lecture of how map and for each can be used in places you don't even think of as being collections. They're actually also really useful for them. Cool. Other questions? Great. Let's keep going. So we did that. So yeah, you've been hearing me kind of give this rant, right? The whole point, of course, is to make code that does great hardware generators, it's reusable, we design for readability, etc. How does functional programming help us? If there's a common pattern and that pattern matches the construct for functional programming, we might as well use it, right? Because that means there's a really, really nice fit, and it's gonna, not just be less code for you to write, but also people reading it can quickly understand the pattern you're doing there. So when it, improves readability, improves code, makes it simpler, that's great. Um, if it's used over eagerly, sometimes it gets a little harder to read and understand. It can be brittle. Um, for example, to make it more concrete, I find, as I said before, doing something like using map to grab out fields is like a slam dunk almost always. However, when I feel pressure to do zip with index, I often just say screw it and just use a for loop, right? Because you need that index, right, for some reason. And so yeah, so like I said, the kind of considerations are: should you use a for loop instead? Maybe is recursion more clear? I say one or two functional programming operations per line at most. Some of them might say three, but that's really pushing it. Um, your function literal, that little anonymous function inside there, if it becomes a more than one line, just write it separately as a function, name it, and then pull it in. Um, Also, sometimes if you don't want to do that, maybe just use a for loop, right? For loops aren't evil. I am trying to get you away from using var, but there's plenty of uses of for that don't use var. And so yeah, and sometimes a judiciously used var is not the end of the world. But for this course, let's try to see what we can do with immutable and see how you can kind of embrace that and what makes sense. And like I said, it's kind of like training for anything, right? You kind of deliberately overtrain, and that makes the things that are simpler cases seem easier, make that kind of more convenient. Cool. Any other questions? Cool. Okay.